Welcome to Talk Tensors. Imagine for a second that you are an art teacher.
Okay, I can picture that.
Right, and you have this incredibly talented student who can perfectly forge a Renaissance masterpiece, like the brush strokes, the sfumato technique, the precise handling of the lighting. It's all there.
So it's mechanically flawless, basically.
Exactly, mechanically flawless. But if you ask that same student to, say, make the subject smile or maybe shift the light source to the left, they just stare at you blankly.
Because they have absolutely no idea what a smile is.
Right, nor do they possess, like, the conceptual understanding of light direction. They can blindly replicate the statistical distribution of pixels that form the end result, but they don't understand the fundamental building blocks of the scene.
And that was exactly the state of generative artificial intelligence before the concepts in the material we're exploring today were introduced.
Yeah, so on today's deep dive, we are exploring a seminal milestone in machine learning from 2016. It's a breakthrough that asked a truly fundamental question about AI.
Which is, how do we get an AI to genuinely understand the underlying independent components of what it creates without human beings sitting there and painstakingly labeling the data for it?
It's such a perfect framing for what remains one of the most elegant papers in the generative space. I mean, we're talking about InfoGAN, or information maximizing generative adversarial networks.
Yeah, and to truly grasp the paradigm shift this represented, we have to transport ourselves back to the computational and theoretical landscape of 2016.
Which feels like ancient history in machine learning years.
It really does. By that point, generative adversarial networks, which were introduced by Ian Goodfellow and his colleagues just 2 years prior, had completely disrupted the field.
Right, the whole architecture set up this brilliant minimax game.
Exactly. You had a generator network taking random noise and mapping it to an image space, basically trying to create fakes.
And pitted against it was the discriminator network, acting as a binary classifier, trying to distinguish the real training data from the generator's fakes.
Through this adversarial tug-of-war, the generator learned to produce startlingly realistic outputs. But the field was hitting a massive, seemingly insurmountable wall when it came to unsupervised representation learning.
Because we had oceans of unlabeled data, right? Millions of images just sitting on servers.
Yeah, but earlier methods and even the standard vanilla GANs of the time were generating what researchers called entangled representations.
To bring this back to the physical world for you listening, imagine you're sitting in the cockpit of a highly advanced airplane.
Okay, a highly advanced airplane, but with a terrible user interface.
Oh, the worst user interface. You look at the control panel, and instead of a distinct throttle, a steering yoke, and a flap switch, you just have 100 identical unlabeled knobs.
Just a wall of random knobs.
Yeah, and here's the kicker. Turning just one knob randomly affects the altitude, the radio volume, the cabin lights, and the landing gear, all at the exact same time.
So you can theoretically fly the plane if you find the exact right combination of knob turns, but you have absolutely no meaningful isolated control over how you fly it.
Exactly. That lack of control meant the AI had just learned a highly complex, convoluted mathematical mapping from a latent space to a realistic image.
But it hadn't discovered the natural joints of the data, as we say.
Right. So today, our mission is to unpack the brilliant architecture that solved this entanglement bottleneck.
The researchers achieved this by literally splitting the input noise vector and using a rigorous mathematical formulation borrowed from information theory.
Which is so cool. We're going to examine the methodology, the integration of mutual information, and the specific tensor behaviors on datasets from MNIST to CelebA.
And, how this architecture laid the groundwork for the controllable AI systems dominating the landscape today.
So let's start with the philosophy of disentangled representations. What does it actually mean, mathematically and practically, for a machine to understand data in an unsupervised context?
Well, the goal of representation learning is to take raw, high-dimensional data like the raw pixel values of an image and embed it into a lower dimensional space.
Where the important semantic features are exposed as easily decodable independent factors?
Precisely. Think about a dataset of human faces. If an AI has a useful disentangled representation, it automatically allocates separate orthogonal dimensions in its latent space for specific physical traits.
Right, so one vector controls facial expression, another independent vector controls eye color, another handles the lighting angle, and so on.
And the downstream utility of this is just massive. Unsupervised learning is inherently difficult because at the time of training, you don't know what specific task you will eventually use the model for.
You're merely trying to find the intrinsic structure of the data manifold.
Yeah, if you can learn a disentangled representation, you are pre-packaging the data in a way that makes future supervised tasks trivially easy.
Because you wouldn't need a million labeled examples to teach a system to recognize a happy face, right?
Exactly. If the system's unsupervised pre-training has already mapped the smile feature to a single distinct axis in its latent space, you'd only need a handful of labels to point the classifier to that specific axis.
But I have to ask, why couldn't a standard generative model just figure this out naturally?
It seems like it should, right?
Yeah. I mean, if a vanilla GAN is mapping random noise to a photorealistic face, and it's optimizing its weights to perfectly mimic the training distribution, wouldn't a clean, disentangled internal representation be the most efficient way for the network to organize its own internal weights?
You would think so, assuming neural networks prefer elegant solutions, but that gets to the core mathematical flaw in the vanilla GAN formulation.
Which is the noise vector itself.
Right. In a standard GAN, you start with a noise variable. This is typically a vector of incompressible, highly unstructured noise.
Like maybe 100 random numbers drawn from an isotropic Gaussian or a uniform distribution.
Yeah, and the generator network takes that noise vector and passes it through a series of transpose convolutions to output a sample. The critical issue is that the objective function places absolutely no restrictions on how the generator utilizes that noise.
It's just a mapping function optimizing for a single scalar value, which is the discriminator's loss.
Precisely. The generator's singular mandate is to fool the discriminator. To achieve that, it will twist, fold, and contort that random noise vector in the most highly entangled way possible.
Because it just takes the path of least resistance through the lost landscape.
It does not care if the internal parameterizations make sense to a human observer at all.
So you change the first scalar value in that 100-dimensional noise vector, and because of the dense, fully connected layers early in the generator, that tiny change cascades through the whole network.
Exactly, simultaneously altering the gender, rotation, and background color of the generated face all at once.
Looking at the historical context of the 2016 era, researchers definitely knew this was a problem. But the prevalent solutions at the time felt like they were circumventing the core issue rather than actually solving it.
Yeah, models like the Deep Convolutional Inverse Graphics Network or DCIGN and various bilinear models were achieving disentanglement, but they required explicit, heavy supervision.
They were basically mathematically holding the model's hand.
They really were. With DCIGN, you had to curate your training batches meticulously. You had to show the model pairs of images and explicitly define the relationship.
Like telling it, these two images share the identical identity vector, but their lighting vectors differ.
Right. You were forcing the disentanglement by structuring the input data and the loss function around human-provided labels.
But in real-world scenarios, data is messy and unstructured. The holy grail of representation learning was to achieve this completely unsupervised.
To just unleash an algorithm on a massive, uncurated folder of images and have it autonomously discover the semantic axes.
Which brings us to the breakthrough methodology of InfoGAN, which is injecting formal information theory into deep learning.
The researchers introduced a major architectural shift here, but it begins with a conceptually simple division of labor.
Yeah, instead of feeding the generator one massive unstructured noise vector, they split the input space into two distinct components.
The first component is the traditional noise vector. It remains the source of incompressible noise, tasked with handling all the random, highly entangled background variations.
So like the exact pixel texture of a brick wall, or the stochastic placement of a stray hair?
Exactly. And then the second component is the latent code. This vector is specifically targeted at capturing the salient, structured, semantic features of the data distribution.
And it isn't just a single vector, right? It can be partitioned into multiple independent codes, which can be a mix of continuous and discrete variables.
Yeah, it creates a bifurcated input topology. You are signaling to the network, hey, this is your entropy source for the messy details, and that over there represents the clean, independent semantic dials.
However, structurally, introducing this new code to the generator creates a massive optimization trap. We can call it the problem of the lazy generator?
The lazy generator is such a perfect term for it because this is where the standard GAN objective function fundamentally fails this new architecture.
Let's break down the lazy generator because it's super intuitive once you see it.
So in a standard GAN setup, the generator is trained solely via the minimax game against the discriminator, right?
Mm-hmm.
If you concatenate this new structured code alongside the usual noise and pass the combined vector into the generator is completely free to just ignore the new code.
The network can easily find a local minimum where the probability of generating an image given the code is exactly the same as the probability of generating it without the code.
Mathematically speaking, the probability of x given c equals the probability of x.
Let me ground this with an analogy for you. Imagine giving a veteran chef a new, highly specific secret ingredient.
That's our structured code, right?
Yeah, the code is the secret ingredient.
Mm-hmm.
And you give it to them along with their standard massive pantry of ingredients, which is the unstructured noise.
Okay, I like where this is going.
If that chef is only being evaluated by a food critic, the discriminator on whether the final dish tastes like an authentic classic meal, the chef has no incentive to use the new ingredient.
They might just look at your secret ingredient, toss it directly into the trash, and cook their reliable proven recipe using only the massive pantry.
Exactly. Why risk ruining a dish that already successfully fools the critic just to incorporate an unproven new element?
And that behavior is exactly what manifests during backpropagation. The generator suffers from a localized mode collapse regarding the structured code vector.
Because mapping a structured, constrained code to a complex visual output is computationally harder early in training than just relying on the highly entangled, high-capacity noise vector it already knows how to leverage.
The gradients flowing back to the structured code basically just vanish. So how do you mathematically force the lazy generator to utilize the latent code?
This is the genius part. The authors proposed an information theoretic regularization term. They explicitly mandated the use of the code through the principle of mutual information.
Mutual information is the absolute linchpin of this entire framework. For our listeners who might be rusty on their information theory, we should probably unpack this.
Yeah, definitely. So mutual information measures the reduction of uncertainty in one variable when another variable is observed. It quantifies how much knowing about one variable tells you about another.
To be precise, it's defined using Shannon entropy. The mutual information equals the entropy of the first variable minus the conditional entropy of that variable giving the second one.
So entropy is essentially a measure of unpredictability. If the two variables are completely independent, knowing the second one does not reduce the uncertainty of the first one at all.
Right, which means the mutual information is zero. Conversely, if they are deterministically linked, observing the second variable removes all uncertainty about the first one, maximizing the mutual information.
Applying this to the InfoGAN architecture, the researchers theorized that there must be high mutual information between the latent code and the generator's final output.
What this means in practice is that the information contained in that code cannot be lost or obfuscated during the forward pass of the generation process.
If you look at the final generated image, you should be able to work backwards and confidently deduce what latent code was fed into the network to create it.
Right. If the code was a discrete categorical variable set to state 3, and that state corresponds to a specific digit shape, you must be able to look at the generated image and say, the code vector was definitely set to state 3.
The uncertainty is completely reduced. Going back to the chef is forced to feature the secret ingredient so prominently in the flavor profile that anyone tasting the dish can immediately identify it.
To enforce this, they modified the standard GAN value function. They took the traditional minimax objective, where the generator minimizes the discriminator's accuracy while the discriminator maximizes it, and they subtracted a regularization term,
which was a hyperparameter lambda multiplied by the mutual information between the code and the generated image.
So now the generator is fighting a multi-objective war. It must synthesize an image realistic enough to fool the discriminator, while simultaneously ensuring the latent code is so clearly expressed in the pixel space that the mutual information term is maximized.
But implementing this in deep learning leads to an immediate mathematical roadblock. Calculating the mutual information perfectly requires access to the true posterior distribution.
You need to know the exact probability of the latent code given the generated image.
But in a deep convolutional neural network, where you're passing vectors through millions of parameters and highly nonlinear transformations, calculating that true posterior requires integrating over the entire high-dimensional image space.
Which is completely computationally intractable. You literally cannot compute the exact mutual information.
This is where the paper transitions from brilliant theory to just exceptional engineering. They bypass the intractable posterior using a technique called variational information maximization.
Since computing the true posterior is impossible, they introduce an auxiliary distribution to approximate it. They essentially construct a separate neural network head tasked solely with predicting the latent code from the generated image.
Hold on, I need to push back on this architecture for a second. We already know that GANs are notoriously unstable. You're constantly fighting mode collapse, vanishing gradients, and the delicate balance of the min-max game.
Oh, absolutely. They are famously fragile.
Right. So now you're telling me we are bolting a second guessing game, this auxiliary network, onto a generator that is already fighting a discriminator. It sounds like a hyperparameter nightmare. How does adding a third competing network not instantly cause the entire training process to collapse?
That is the exact skepticism many researchers had when reading the premise. Adding independent networks to a GAN usually spells disaster. But let's look at the mathematical sleight of hand they used to stabilize it.
Okay, lay it on me.
By utilizing this auxiliary distribution, they define a variational lower bound on the mutual information. The derivation relies on the properties of Kullback-Leibler divergence, or KL divergence, which measures how one probability distribution diverges from another.
Right, the KL divergence between the true posterior and our approximation. And because KL divergence is strictly non-negative, it's always greater than or equal to 0, the researchers can mathematically prove that their tractable approximation will always be a lower bound to the true mutual information.
Exactly. The true mutual information is guaranteed to be greater than or equal to this lower bound. Therefore, if you optimize your neural network to maximize this lower bound, you're inherently driving up the true mutual information.
And crucially, this lower bound is highly practical to compute. It doesn't require complex integration. It can be efficiently approximated using simple Monte Carlo simulations.
Let's clarify what that Monte Carlo approximation looks like in the actual code loop.
Yeah, that helps ground it. So during a training step, you sample a batch of random noise vectors and a batch of random codes.
You pass them through the generator to get a batch of fake images. Then you pass those fake images into the auxiliary network and calculate the log likelihood of the network, correctly guessing the codes you originally sampled.
You average that out over the batch, and that gives you your gradient for the mutual information loss. It's elegant and computationally cheap.
But to address your earlier pushback about the network collapsing under the weight of too many moving parts, we really have to look at how they engineered this auxiliary network.
Because when you hear, we need an auxiliary distribution to guess the latent codes from the pixels, you might assume they had to build and train a third massive convolutional neural network alongside the generator and the discriminator.
And if they had done that, the compute costs would have doubled and the training dynamics would have likely shattered.
But they didn't build a third network from scratch. This is the structural genius of InfoGAN. The discriminator is already doing the heavy lifting of extracting visual features from the images to determine if they are real or fake.
Right. It has deep convolutional layers that have already learned to identify edges, textures, shapes, and structural coherence.
So instead of building a separate deep network, they just hijack the discriminator's feature extractor. The discriminator and the auxiliary network share almost all of the same convolutional layers.
It's just a single trunk. At the very end of that trunk, it branches off. One tiny, fully connected layer outputs the scalar for the real or fake discriminator guess, and another tiny, fully connected layer outputs the parameters for the auxiliary distribution.
The efficiency of that shared architecture cannot be overstated. It means you're achieving a disentangled, highly interpretable latent representation for practically zero extra computational cost compared to a standard GAN.
The marginal cost of adding one fully connected layer to predict the code is computationally negligible.
Furthermore, because the auxiliary network is piggybacking on the discriminator's feature extraction, it stabilizes the training.
Yeah, the representations learned by the discriminator to spot fake images are highly useful for the auxiliary network to isolate the semantic features.
And the gradients from the auxiliary network forcing the network to recognize semantic features actually help the discriminator learn better representations. They become mutually beneficial.
This mechanism, using an auxiliary network to infer latent variables from generated data to train the generator, isn't entirely isolated in the history of machine learning, though.
Right. The authors explicitly draw a lineage connecting variational information maximization to the wake-sleep algorithm.
Which, for those who study the history of neural networks, takes us all the way back to 1995, to Geoffrey Hinton, Peter Dayan, and their work on Helmholtz machines.
The historical parallel is fascinating because it highlights how theoretical concepts often wait decades for compute power to catch up. In the classic wake-sleep algorithm, you had two distinct phases.
The wake phase involved updating the generative model's weights based on real data to better model the environment.
And the sleep phase involved updating the recognition model, the network trying to infer the hidden causes or latent variables, by having the generator dream up fake samples.
The recognition model learned by trying to deduce the hidden variables that the generator used to create the dream.
The problem in the 90s was that the wake-sleep algorithm didn't strictly optimize a single bound, and the lack of advanced backpropagation frameworks made it difficult to scale deep architectures.
But InfoGAN essentially modernizes this. When we optimize the surrogate loss with respect to the auxiliary network, it is exactly equivalent to the sleep phase.
The generator is dreaming up images from sampled noise and codes, and the auxiliary network is learning to recognize those latent codes from the dreams.
But the authors note a crucial upgrade here. In InfoGAN, the generator is also updated during this phase to maximize the mutual information lower bound.
Because both the generator and the recognition network are updating their weights simultaneously based on the AI's internal dreams, completely decoupled from the labeled reality of the training data, the researchers playfully refer to it as a sleep-sleep algorithm.
It's a self-contained optimization loop driven entirely by information theory.
Okay, so the math is rigorous, the derivation of the lower bound is sound, and the shared convolutional architecture solves the compute issue. But a theoretical lower bound is still just an approximation.
Right. Did this actually survive contact with messy, real-world pixels?
Exactly. Let's dive into the experimental results, starting with the baseline proving ground of all computer vision, the MNIST dataset.
MNIST, the massive database of handwritten digits from 0 to 9, is perfectly suited for this because we intimately understand its latent structure.
We know there are 10 discrete numerical classes, and we know handwriting varies continuously in terms of slant and stroke thickness.
To map this, the researchers configured the latent code to have 3 distinct variables. First, a discrete categorical variable modeled to take on 10 distinct states.
And second and third, 2 continuous variables modeled as uniform distributions ranging from -1 to +1.
The very first question the paper had to answer was, does the lower bound actually maximize? Does the mutual information get captured, or does the generator still find a way to be lazy?
And the empirical answer was a resounding yes. The lower bound quickly maximized to roughly 2.30.
And why is 2.30 significant? In information theory, the maximum entropy for a uniform 10-state discrete variable is the natural logarithm of 10, which calculates to approximately 2.30.
This mathematical convergence proved that the generator wasn't ignoring the discrete code, it was utilizing it perfectly, and the auxiliary network was extracting it flawlessly.
But the tensor visualizations are where the theoretical math translates into intuitive magic.
Let me describe this visually for you. Imagine a row of generated images. As you step the discrete variable from state 0 through state 9, the model naturally cycles through the digits.
It generates a 0, then a 1, then a 2, all the way to 9. The model effectively partitioned its latent space into 10 distinct clusters corresponding to the 10-digit identities.
And what is truly profound is that it achieved a 5% error rate on classifying MNIST digits without ever being provided a single label during training.
It just observed the statistical distribution of pixel densities and deduced, hey, there are 10 distinct topological shapes occurring frequently here. I will unilaterally map my 10-state discrete dial to these 10 shapes.
It discovered the semantic concept of numerical taxonomy purely through unsupervised observation. But then we examined the continuous codes. What did those smooth, uniform variables learn to represent?
The network autonomously assigned the first continuous code to control the rotation or slant of the digit.
As you smoothly interpolate it from -1 to +1, the generated digit smoothly tilts from leaning heavily left to leaning heavily right while maintaining the identity of the digit.
Furthermore, the second continuous code autonomously learned to govern the stroke width.
And crucially, the way it handles stroke width proves it is learning semantics, not just performing a mechanical pixel stretch.
Yeah, if you take an image of an 8-myth and apply a crude horizontal stretch in photo editing software, you distort the entire image. blurring the empty spaces inside the loops of the 8.
But when InfoGAN sweeps the continuous variable to widen the digit, it intelligently adjusts the stroke thickness while preserving the structural integrity of the loops. It thickens the ink without filling in the holes.
The researchers even pushed the model to extrapolate. They trained the continuous sliders from -1 to 1. But during inference, they pushed the vectors all the way to -2 and +2.
Extrapolation is a massive test for any neural network. Typically, if you push a model outside its training distribution, it produces garbage.
But InfoGAN generalized perfectly. It continued to rotate the digit further or make the ink even thicker in a mathematically consistent way that still resembled natural handwriting.
This proved the representation was genuinely modeling the underlying physical concepts of rotation and thickness, rather than just memorizing data points from the training set.
However, MNIST is a simple 2D monochrome dataset. A multi-layer perceptron can brute force MNIST. To truly prove the robustness of variational information maximization, they had to tackle higher dimensional 3D data manifolds.
So they moved to a dataset of 3D rendered faces.
This is where we compare InfoGAN against the supervised cheating we discussed earlier. Prior models required explicit pairing to learn 3D poses.
You had to feed the network a tensor of a face looking left and a corresponding tensor of the exact same face looking right. InfoGAN enters the 3D face dataset completely blind. It only sees a randomized pile of pixels.
Yet, despite the lack of paired data, the continuous latent codes in InfoGAN natively mapped to the exact same 3D spatial properties.
One continuous vector became the dedicated dial for azimuth, the pose of the face rotating smoothly from left to right.
Another independent vector mapped seamlessly to elevation tilting the face to look up toward the camera versus looking down.
A third vector mapped flawlessly to the spatial direction of the light source, sweeping shadows dynamically across the topography of the face.
The isolation of those features is impressive, but the true power of unsupervised representation learning lies in data discovery.
Because InfoGAN isn't constrained by predefined human labels, it can unearth latent variables that the researchers didn't even conceptualize.
During the 3D face experiment, the model found a continuous latent code that smoothly interpolated the facial structure from wide to narrow.
That is the crucial detail. Facial width was not a feature the researchers explicitly labeled or tested for in prior supervised benchmarks.
The AI simply analyzed the variance in the dataset and mathematically determined that the structural width of the face represents a fundamental orthogonal axis of variation.
It shows how these networks can reveal hidden dimensional structures within our own data that human bias might overlook.
They replicated the success on a 3D chairs dataset too, seamlessly capturing rotation and natively morphing a standard narrow dining chair into a wide plush armchair.
But again, rendering 3D models against a clean black background is a sterile environment. The real test of an unsupervised representation is its resilience to unstructured chaos.
To test this, the researchers evaluated InfoGAN on the Street View House Number dataset, or SVHN.
For context, working with SVHN is notoriously painful. These are cropped RGB photographs of house numbers taken from Google Street View cars. The resolution is highly variable.
You have severe compression artifacts, bizarre real-world lighting, reflections, and the most challenging element, distracting, irrelevant background digits.
You might be trying to classify a central digit 3, but the crop includes a blurry 1 encroaching on the left side and a partially obscured 4 on the right.
It is a dataset defined by its noise. When a standard GAN generates SVHN images, it entangles the central digit with the background clutter.
But InfoGAN handled the chaos with remarkable elegance. The model allocated a continuous code to isolate the variable lighting conditions.
More impressively, it utilized a discrete categorical code to map the central digit and a completely separate set of continuous codes to control the background context independently.
Wait, how does it differentiate between the central digit and the background digit if it has never been taught the concept of a background or a subject?
It comes down to the frequency and spatial distribution of the variance. The central digit is always roughly in the middle, and its structural variations are highly consistent across the dataset.
While the background clutter is highly variable in placement and structure.
Right. The mutual information objective forces the auxiliary network to find the most predictable, reliable ways to extract the codes.
So it is mathematically easier for the network to assign one discrete variable to the highly structured central variance and assign different variables to the messy peripheral variance.
Rather than trying to entangle them into a single code, exactly.
Yeah, so you could literally turn a latent dial keeping the central 3-foot perfectly statically identical, but swap out the blurry background 4-one on the edge for a different texture entirely.
It natively learned to disentangle the subject from the context, which leads us to the final, most complex experimental domain, CelebA.
CelebA consists of over 200,000 celebrity faces captured in the wild. The background clutter is immense: red carpets, crowds, varied indoor and outdoor lighting.
Subjects are wearing hats, their hands are obscuring their faces, their hair is blowing in the wind.
And critically, unlike the 3D face dataset, CelebA does not contain perfectly matched poses. You do not have an image of a celebrity looking left and a mathematically matched image of that same celebrity looking right.
The data manifold is highly irregular, and yet InfoGAN managed to untangle the mess.
Despite the sheer chaos of the dataset, the architecture successfully disentangled azimuth head rotation, with the same precision it achieved on the clean 3D faces.
But it went much further into specific human semantics. It isolated a continuous dial for the presence of eyeglasses.
As you slide the latent vector, frames naturally materialize on the generated celebrity's face, complete with proper shading and glass reflections.
It isolated a dial for hairstyles, smoothly transitioning a generated face from having tight, short hair to voluminous long hair.
And perhaps most impressively, it mapped human emotion. It created an independent latent vector that transitions a facial expression from a stern, neutral gaze to a wide, happy smile.
All without altering the underlying identity of the face or the ambient lighting in the background. Your hypothetical art student finally understood the independent concept of a smile, derived entirely from the statistical distribution of unsupervised data.
But wait, why did the model choose a continuous variable for eyeglasses? Intuitively, glasses are a binary, discrete object. You either have them on or you don't. But hair length is a continuous spectrum.
That's a brilliant question about how the latent space maps to pixel space. Even though eyeglasses are a discrete object, the appearance of eyeglasses in a dataset is continuous.
Oh, because of the thickness of the frames, the opacity of the lenses, the gradient of the shadows they cast, these vary smoothly across the dataset.
Exactly. When the auxiliary network is forced to maximize mutual information with a continuous code vector, it maps that vector to the most prominent feature that exhibits a smooth gradient of change.
Hair volume and the opacity of eyeglasses both present smooth, high-variance gradients in the pixel space, so the continuous codes naturally latch onto them.
If we synthesize the overarching narrative of this deep dive, InfoGAN remains a titan in the literature because it proved that unsupervised, disentangled representation learning was not just a theoretical pipe dream.
It was practical, it was scalable to deep convolutional architectures, and thanks to the shared layer engineering, it was computationally lightweight.
It fundamentally shifted how the field approached latent spaces. When we examine the modern AI ecosystem, when you utilize a diffusion model to generate an image, or when researchers manipulate the latent space of large language models,
the foundational premise that a neural network's internal representations can be mathematically coerced into human interpretable, independent orthogonal vectors owes a massive debt to this paper.
The controllable AI we leverage today, the ability to prompt a system to alter a specific feature without destroying the entire output, is built on the intellectual legacy of understanding and manipulating these latent codes.
We do have to acknowledge the technical limitations, though. InfoGAN is not without its flaws. The hyperparameter lambda, which scales the mutual information term, requires careful tuning.
Yeah, if lambda is too high, the generator obsesses over making the codes obvious and degrades the visual realism of the image.
Furthermore, because InfoGAN relies on the foundational Jan minimax game, it inherits the classic Jan training instabilities.
The generator and discriminator can still fall out of equilibrium, leading to mode collapse, even if the mutual information lower bound converges quickly.
It is not a silver bullet, but it was a massive necessary leap forward in the interpretability of deep neural networks.
Which brings us to the segment of the deep dive where we take these foundational concepts and push them to their theoretical limits.
It is time for novel notions. Please note, the following ideas are purely theoretical, highly speculative, and designed for entertainment and thought experiment purposes only.
We are taking the core mechanics of InfoGAN utilizing variational mutual information maximization to force unsupervised disentanglement and projecting them into the future to see what outlandish yet logically plausible research architectures we can architect on the fly.
I'll pitch the first concept. I call it InfoBCI, or Brain-Computer Interface Disentanglement.
Taking mutual information from the spatial domain of pixels into the temporal domain of neurology. I'm intrigued. Walk me through the problem state.
Currently, we struggle immensely with non-invasive brain-computer interfaces, specifically EEG caps that read electrical signals through the human scalp.
The fundamental bottleneck is that the human brain is an incredibly noisy environment.
Exactly. You are trying to isolate a faint, specific electrical signal, say the motor intent telling a digital cursor to move to the left. But that tiny signal is buried under an avalanche of biological static.
Your heartbeat, your breathing, your digestion, your baseline stress level, the microtension in your jaw muscles.
The raw EEG readout is a highly entangled mess of multi-channel time series data. What if we applied the exact auxiliary network mutual information maximization from InfoGAN to real-time brainwave streams?
We would need to define the tensor topology carefully. We treat the raw, continuous stream of multi-channel EEG data as the output of a generative process.
We split the architecture's latent space, just like InfoGAN. The incompressible noise vector represents the biological static, the autonomic nervous system background hum that varies unpredictably from moment to moment.
And the structured latent codes are forced to represent the discrete, intentional cognitive states. Let's design the architecture.
We take 100 subjects and fit them with high-density EEG caps. We have them play a simple, fast-paced video game like Pac-Man for several hours. We record hundreds of gigabytes of raw, multi-channel EEG data.
But here is the critical constraint. We do not label a single millisecond of it. We don't use timestamps to map brainwave state A to joystick moved left.
We just feed the raw, chaotic brainwaves into an InfoGAN-style 1D convolutional architecture.
The generator in this scenario is a network tasked with synthesizing realistic 500 millisecond windows of EEG data. The discriminator tries to distinguish the AI-generated brainwaves from the real human brainwaves.
But we introduce the auxiliary network. We define the code to include a four-way discrete categorical variable, hypothesizing it will map to the four directional intents: up, down, left, right.
We also include a continuous variable, hypothesizing it might map to cognitive load or focus. We force the generator to reconstruct the brainwave patterns while maximizing the mutual information specifically with those codes.
The auxiliary network reads the 500 millisecond EEG window and has to output the correct four-way discrete classification.
Exactly. What is the loss function forcing here? To successfully fool the discriminator while simultaneously maximizing the information in the code, the generator cannot encode the code variable into the random stochastic noise of a heartbeat.
Because the auxiliary network would never be able to reliably recover it from the variance.
The network will be forced to automatically isolate the pure recurring signal of human intent from the biological noise.
Because the neurological intent to move the joystick left is a highly structured, semantically consistent feature across the dataset, the mutual information objective will naturally map it to the discrete code.
If the optimization holds, we could examine the learned codes after training and find that without a single supervised label, the continuous latent code natively mapped to the user's fluctuating focus level.
While the discrete code perfectly isolated the directional movement intention, you would effectively isolate the pure signal of human intent from the biological static.
It would make non-invasive BCIs exponentially more accurate and completely self-calibrating. A new user just puts the cap on, plays a game for 10 minutes to let the unsupervised info BCI map their personal latent neurological space, and the system locks in.
It takes the disentanglement out of pixels and applies it to biological time series data. The map doesn't care if it's processing the width of a handwritten 7 or the amplitude of a beta wave. All right, pitch me the second novel notion.
Let's transition from brainwaves to language. I call this semantic infodecoders for LLMs.
Applying this to large language models. Set the scenario.
Currently, the latent spaces of large language models are notoriously entangled. If you prompt an LLM to rewrite a complex paragraph to be more polite, the model often inadvertently alters the factual content, or it drastically reduces the length and detail of the response.
The semantic feature of politeness is heavily entangled in the model's weights, with verbosity and factual density.
The current industry solution to this is RLHF reinforcement learning from human feedback.
Right. RLHF is effectively the modern equivalent of the supervised cheating we discussed with the old 3D face models.
We are manually paying human raters to read outputs and label them, telling the model, this output is polite but wrong, this output is rude but factually accurate.
It is incredibly expensive, time-consuming, and notoriously brittle. So how do we design an InfoGAN architecture to fix an autoregressive LLM?
We apply the variational mutual information framework directly to the LLM's decoding process. Generating text is discrete, not continuous like pixels, so we'd have to use a differentiable approximation like the Gumbel softmax trick to pass gradients through the discrete text tokens.
We train a secondary generative text layer, an adapter on top of a frozen base LLM. During the generation of a response, at each token step, we inject a continuous latent code into the decoding stream.
And just like in InfoGAN, we need the auxiliary network. We deploy it, perhaps a smaller, highly efficient pre-trained model like Roberta that reads the final complete generated paragraph and is tasked with regressing the continuous value of the code that was injected during generation.
We enforce a massive mutual information penalty during training.
Precisely. We just let the LLM generate millions of responses across diverse topics. The base model ensures the text is coherent and factual. But the adapter layer is constantly being forced to manipulate the output text so that the auxiliary network can accurately predict the value of the code.
The expected outcome is that the adapter must autonomously disentangle abstract human concepts to survive the training objective.
It has to invent ways to vary the text that are consistent, measurable by the auxiliary network, and completely independent of the core factual content.
Without a single human providing a label or a thumbs up, the model might organically create a perfect, isolated continuous dial for sarcasm, another independent dial for formality, and another for reading level complexity.
It would fundamentally alter prompt engineering. You wouldn't need to write convoluted prompts like, please explain this concept like I am a 5-year-old, and employ a slightly sarcastic tone.
You would simply prompt the base model for the factual output, and then manually adjust the decoupled latent vectors. You turn the reading level dial down to 0.1 and turn the sarcasm dial up to 0.8.
The mathematical bounds of the infodecoder would guarantee that adjusting those specific dials alters only the semantic tone, leaving the factual accuracy completely untouched.
It would be true. Controllable, disentangled text generation achieved purely through unsupervised information theory, entirely bypassing the bottleneck of human feedback.
It serves as a testament to the enduring, fundamental power of this 2016 architecture. The exact mathematical principles utilized to separate the rotation of a handwritten digit from the thickness of the pen stroke could theoretically be adapted to separate the hard facts of a sentence from the underlying sarcasm of its delivery.
Information theory is universal.
And that universality is precisely why we dive deep into the foundational classics of the field. Thank you for going on this technical journey with us. As always, the link to the original InfoGAN paper is available in the description below.
We highly encourage you to examine the visual grids in the paper for yourself. It is one thing to hear us describe the tensor outputs and the faces rotating, but it is another experience entirely to see the mathematical disentanglement rendered in print.
It is always a pleasure to unpack these foundational ideas and trace their impact on the current state of the art.
As you go about your day, we want to leave you with a conceptual thought to mull over. We have discussed at length how artificial intelligence can utilize mutual information to discover hidden, independent dials for physical traits like smiling or chair width or digit rotation.
Consider your own daily routine, your habits, your fluctuating moods, your rapid decisions. If an InfoGAN architecture were trained purely on the unlabeled high-dimensional dataset of your daily life, what unseen latent codes would it discover?
What are the fundamental independent dials that are truly controlling your behavior that you haven't even managed to put a conscious label on yet?
Keep diving deep, and we'll see you next time.